melatonin's reputation as the sleep hormone belies a more intricate reality. While melatonin levels do rise as darkness falls, it's not a direct trigger for sleep. Your suprachiasmatic nucleus, a tiny brain region, orchestrates this rhythm. It sends signals that adjust melatonin production in the pineal gland. However, melatonin acts more like a dimmer switch, not an on-off button. Its role is to signal the body's readiness for rest rather than induce sleep. This dimming effect is why you can still stay awake despite high melatonin levels. The real sleep inducer is adenosine, building up with every waking hour. The buildup of adenosine in your brain parallels your wakefulness. Every moment you're awake, adenosine accumulates, binding to receptors that gradually increase sleep pressure. This biochemical process explains why caffeine, an adenosine antagonist, keeps you alert. It blocks these receptors, masking your brain's sense of fatigue. This invisible buildup peaks in the late evening. It's a biological crescendo that propels you towards sleep. Interestingly, the longer you defy this buildup, the more profound the eventual sleep need becomes. Adenosine's role is critical, and unlike melatonin, it directly influences your ability to fall asleep. Your circadian rhythm is not merely a sleep-wake cycle. It's a complex network of genes and proteins. Key players include the PER and clock genes, which regulate cycles of cellular activity. These proteins oscillate in concentration over roughly 24 hours, dictating fluctuations in alertness and fatigue. Surprisingly, light exposure can reset this molecular clock, altering your sleep pattern. That's why late-night screen exposure can disrupt sleep, delaying melatonin release. This genetic machinery is ancient, having evolved to align with the Earth's rotation, demonstrating how deeply circadian rhythms are embedded in our biology. Sleep isn't static, it's divided into distinct stages. Non-REM and REM sleep cycles are pivotal to nightly rest. Non-REM sleep, particularly stages 3 and 4, is where the deepest rest occurs. It's known as slow-wave sleep, characterized by delta waves. During this phase, your body repairs tissues and strengthens the immune system. REM sleep, the stage linked to vivid dreaming, is vital for memory consolidation. Each cycle lasts about 90 minutes, repeating throughout the night. Disruption in these cycles, such as waking during REM, can lead to feeling unrested. Understanding these stages reveals sleep's architecture. Stress-induced cortisol is a notorious sleep disruptor. Cortisol peaks early in the morning, known as the cortisol awakening response, energizing you for the day. But elevated evening cortisol, often due to stress, can delay sleep onset. This delay occurs as cortisol antagonizes melatonin, hindering its dimming effect on wakefulness. Chronic stress keeps cortisol elevated, misaligning your natural sleep-wake cycle. This can lead to a cascade of sleep difficulties, further amplifying stress. Understanding cortisol's timing helps explain the biochemical tug-of-war that can keep you awake at night. It's a crucial piece in the puzzle of sleep onset. In the intricate dance of sleep regulation, adenosine kinetics play a starring role. Adenosine, a byproduct of ATP metabolism, accumulates in the basal forebrain. This buildup is a biological marker of wakefulness. The more adenosine accumulates, the greater the sleep pressure becomes. In 2005, a study in the Journal of Neuroscience showed adenosine receptor activation increases in sleep-deprived states. This activation enhances the need to sleep. Caffeine's molecular structure mimics adenosine, competitively binding to these receptors. By blocking adenosine, caffeine tips the balance towards wakefulness, revealing the delicate chemistry at play inside your brain. While you sleep, the glymphatic system springs into action. This cerebrospinal fluid network clears waste from the brain, including amyloid beta peptides. A 2013 study in Science identified this system as more active during sleep than wakefulness. Glymphatic clearance peaks during deep sleep, where slow-wave activity facilitates fluid exchange. This waste removal is crucial. Impaired clearance is linked to neurodegenerative diseases. The brain's self-cleaning mechanism underscores why adequate deep sleep is vital. This process highlights how sleep isn't just a passive state, but an active maintenance period, rejuvenating the brain at a cellular level. Circadian oscillator genes like clock and BMAL1 form the backbone of our sleep-wake cycle. These genes are expressed in nearly every cell, oscillating over 24 hours to regulate physiological rhythms. Clock and BMAL1 proteins dimerize, initiating transcription of target genes. This transcriptional feedback loop impacts processes from metabolism to hormone release. Light exposure can reset this clock, altering gene expression and subsequently, your sleep cycle. A 2017 Nature Reviews Molecular Cell Biology study underscored the clock gene's role in adjusting circadian rhythms. Understanding these genetic mechanisms reveals how deeply we are wired to Earth's cycles. The cortisol awakening response is a burst of hormone release that primes you for the day. Within 20-30 minutes of waking, cortisol levels surge by 50-60%. This surge is critical for mobilizing energy reserves and heightening alertness. A 2018 study in psychoneuroendocrinology documented this effect across diverse populations. However, chronic stress can lead to dysregulation, causing evening cortisol elevation. This misalignment with natural rhythms can delay sleep onset. Cortisol's precise regulation is a testament to the delicate hormonal balance required for optimal sleep architecture. Disruptions in this rhythm can have profound effects on sleep and wakefulness. REM stage sleep is the neural playground for memory consolidation. During this stage, the hippocampus actively replays recent experiences, integrating them into long-term storage. This synaptic reinforcement occurs through theta wave activity. A 2021 Nature Communications study showed theta activity is crucial for linking memories. REM's unique architecture also fosters creativity by connecting disparate ideas. This is why REM deprivation can impair problem-solving skills. The intricate processes of REM highlight sleep's role in cognitive function. Understanding REM's place in sleep stages reveals how each phase contributes uniquely to brain health. Chronic sleep debt is more than occasional insomnia. It's a cumulative physiological burden. A 2017 study in sleep found that even partial sleep restriction can lead to cognitive impairments over time. Unlike acute deprivation, which shows immediate deficits, chronic debt accumulates silently. It affects attention, mood, and metabolic health. What's insidious is this debt accrues without immediate noticeable signs, lulling many into underestimating its impact. This accumulation affects your brain's ability to regulate emotions, making stress harder to manage. Chronic sleep debt highlights the importance of understanding sleep as a long-term investment in health. Sleep tracking apps offer a glimpse into your sleep habits, but they lack the precision of polysomnography. Polysomnography, the gold standard, measures electrical brain activity, eye movements, and muscle tone. A 2016 Journal of Clinical Sleep Medicine study showed consumer devices often misclassify sleep stages. These devices can overestimate sleep duration by up to 67 minutes. This discrepancy can lead to false assumptions about sleep quality. True insights require understanding sleep architecture, which apps alone cannot provide. The gap between technology and science reveals the nuances of sleep measurement. The wellness industry often touts simplistic solutions for sleep, like blue light glasses or herbal teas. Yet, peer-reviewed literature emphasizes the complexity of sleep regulation. A 2019 study in Sleep Medicine Reviews found limited evidence supporting the efficacy of these remedies. The intricate interplay of neurochemicals and genetic factors defines sleep quality. While lifestyle changes can aid sleep, they must align with biological rhythms to be effective. This mismatch between commercial advice and scientific understanding demonstrates the need for evidence-based approaches. Sleep's complexity defies one-size-fits-all solutions. Acute sleep deprivation affects your brain's connectivity. A 2018 Nature Communications study revealed changes in the connectivity of the default mode network after just 24 hours of wakefulness. This network is crucial for introspection and memory. Disrupted connectivity correlates with impaired cognitive function and emotional regulation. These effects can mimic those seen in chronic sleep conditions. Even short-term deprivation leaves a measurable impact on neural function, underscoring the brain's sensitivity to sleep loss. The rapid onset of these changes highlights the urgent need for adequate rest. A 2020 PLOS Biology study quantified sleep's impact on metabolism, showing a 30% reduction in insulin sensitivity after 5 nights of sleep restriction. This finding reframes sleep as a metabolic regulator. Poor sleep can lead to insulin resistance, increasing the risk for type 2 diabetes. This metabolic dimension of sleep underscores its systemic importance beyond rest. The study's controlled conditions revealed how even moderate sleep loss can disrupt glucose metabolism. This highlights the intricate relationship between sleep and metabolic health, challenging the notion that sleep is merely restorative.